Okay, so in this next video, we're going to consider what happens when we discharge a line or disrupt the steady state that has built up. In the last video, we talked about what is the steady state if we wait for t equals infinity after connecting a new voltage. And now we're going to consider what happens when we break that steady state. All right, so let me go back to this simple circuit of you've got a voltage connected to a generator resistor and connected to a long transmission line. And our assumption right now is that this voltage has been connected to the circuit for a very long time, long enough that we've gotten ourselves to an equilibrium state. And at that equilibrium state, we know there is a positive going voltage, V positive. After all those positive going waves add up on top of each other, the net total is V positive, and all the negative going waves, V negative, that go in the other direction add up to something else. And we know how to calculate what V positive and V negative are. V positive equals VL plus Z0 IL over 2. And V negative equals VL plus, oops, sorry, that's a minus right there. VL minus Z0 IL divided by 2. All right. So now we're going to consider a situation where at t equals 0, there's a switch here that's going to open. All right. When that switch opens, it's going to detach the source from the rest of the circuit. All right. So we're no longer going to be pumping in that V positive anymore. All right. So let's consider what's going to happen in this case. And let me go back to the analogy of the source being like a spout of water that's spitting water into a pipe or into a groove where you have waves of water, right? And everything is sort of flowing in a circle. You have some water escaping because of dissipation on both ends, but you're also adding more water at the source. And so when we have this circle of water that has reached equilibrium, and all of a sudden we shut off the source, all right? The first question to ask is what's going to change, right? We got at the source, there's V positive and there's V negative, right? Now think about this for a second. There is V negative, right, which is a negative going wave, which is working its way over here. And that water is coming from the load. And nothing at the load has changed. Nothing along the transmission line has changed. And so even if you shut off that power at the hose or you turn off the water at the hose, there's still water coming down from the load that you can't stop yet. It's going to take some amount of time for that basically offing of the water to go back and forth and reach you again. So the moment you turn off the water, nothing happens to V negative. That's the key, right? So at t equals V positive, there is no change to V negative, right? That's the most important thing. Because again, V negative is only established as a result of positive going waves reaching the load, reflecting and coming all the way back. And that hasn't changed, right? That's going to take some time. So the moment that we open the switch and remove the load, the only thing that's going to change is V positive, okay? So V positive will change at t equals 0. And that's the key, right? We now have to ask the question, given that we understand that V positive is going to change because that's where the break is occurring, right? The break is occurring right here. So given that V positive is going to change, what is it going to change to? So all of our circuit line understanding is still going to hold in that V positive is going to be made up of two pieces. The first piece is the negative going wave that reflects, and the second piece is the voltage that's being injected by the generator. The first piece is still there, it hasn't changed, but the second piece has. And so our new V positive, which I'm going to write down, V positive new, is going to be equal to V negative times our new value of the generator reflection coefficient. okay? What is gamma G nu? The reflection coefficient at the generator side will be what it will be established after we open the switch. So when we open the switch, the transmission line ends up with an open circuit, right? An open circuit has a value of gamma G of +1, okay? So that just means that V positive nu, in this case, is just the same as V negative. Remember, V negative hasn't changed, but V positive has, okay? So we've got an old value of V positive, which we calculated before we started, and we have a new value of V negative, which in this case happens to be the same as V negative. And so with that, we can see that there is a step change that has occurred. So there is basically a delta V positive, which we could write as V new, V positive new minus V positive old, right? This is basically going to be the delta or the change as a result of the opening of that switch, or basically because of the removing of that voltage injection by the generator. And so armed with this information that this is the voltage change that we are creating, from that point on, we can go to a simple bounce diagram and track everything exactly the way we did before. All right, so let me set this up as a simple bounce diagram and just kind of show you. We'll start out with the two lines right here. And we're going to have our load voltages, which is going to start out at our V positive, old, our original V positive. And then we're going to inject a voltage wave into this. That voltage wave is going to be, it's going to have value of delta V positive, right? And we're just going to inject that as if it were a new wave that were being inserted into this transmission line. And that wave is going to work its way down. So this is a delta V positive. It's working its way down the transmission line in the positive direction. We have a reflection coefficient here of gamma L. We also have gamma G nu, which equal 1. When this delta V positive reaches the load, it's going to reflect. We know what the reflection coefficient is. It's gamma L. And so this will be a delta V positive multiplied by gamma L is the value of the voltage wave moving this way. And this will reflect like that. Delta V positive gamma L times gamma G. In this case, gamma G is 1, so it's a little simpler to do that. And that wave is moving this way, and this process will repeat, all right? We can then track what's happening to the load voltage, right? The load voltage start out at V positive old, and once this wave hits and reflects, it's going to change. It's going to be V positive old plus delta V positive plus delta V positive times gamma L. Take the previous value of the voltage on the load, add the incoming wave, and add the reflected wave, and that will be the value of the voltage on the load after that reflection has occurred. And we can continue this process onwards. And what's amazing is that if you repeat this and carry this out to t equals infinity, it's going to get us to the precise steady state condition that we expect. Okay, in this case, we would expect that when we open this switch right here, that eventually there ought to be no voltage, right? Because there's no battery, right? I just have, all I have is a transmission line connected to a resistor and nothing else, right? So I would expect there to be no voltage and no current. And I can promise you that if you continue this process on this bounce diagram, you will get back to V equals 0 and I equals 0 everywhere. It's almost like magic because you haven't told this bounce diagram, where you haven't basically forced everything to reach that steady state, but the math just happens to work out because that's how transmission lines work. And that's what really happens whenever you make a change to a circuit. So let me just sort of first show you a visualization. And then I'm going to sort of recap the steps to solve a problem like this. All right, so let me go back to this problem. And here we've got this is the same visualization that I showed before. It's still playing. I haven't stopped it. So the generator resistor is 50 ohms, the line is 100 ohms, and load is 200. And so we have a V positive and a V negative that are established across this line. We can figure out what that is. But what I'm going to do is I'm going to pause it right here, and I'm going to instantaneously change the load resistor, and I'm going to make it a short circuit. All right. Now, before I press play, let's think about what's going to happen. We've got positive going wave that's going from generator to load, and we've got a negative going wave that's going from load back to generator. Which one is going to change, and where is it going to change the moment that we change that load resistor? Go back to the water analogy, that the generator is like pumping water into a pipe and goes down a pipe, reaches an end, and some of it reflects and comes back, whereas some of the water escapes. And the moment that we change that resistor value to 0 ohms, the water is coming from the generator has not changed, right? That's still coming in, right? We don't have the chance to disrupt that. But what has changed is what that reflection is going back in the negative direction. And so we anticipate that V negative will change at the load, right? V positive is not going to change, and neither one is going to change at the generator side. There's going to be a change to the value of V negative at the generator. Sorry, not a generator, at the load. So let me now press step, and we'll continue that. All right. When I press this step button, you'll see here is a wave that is starting out at the load side, because that's where the change was, and it's going to move in the opposite direction, right? Now, what has changed here? V positive is still the same value that it was before, but V negative now has a reflection coefficient of -1 applied to the voltage. So whatever the V positive was, the newly established V negative is going to be the negative of that, which means the sum total of that is 0. So the voltage, as you see, immediately drops to 0, and the current, in fact, does the opposite. So once we treat this as a negative going wave that starts out at the generator, sorry, at the load, and works its way backwards, we can simply trace this, and you can watch what happens to this wave as it settles out. And this is going to take a few back and forth before it gets there. Watch, but here's a wave that's reflecting. The reflection coefficient at the generator is not 0, so there's going to be some back and forths here. But watch, this is slowly going to establish the steady state condition that we expect. Remember, the orange line is the current, and the darker red is the voltage. And if we wait long enough, we're going to see the voltage is going to work its way towards 0, as it should. Right? There ought to be no voltage. The current is increasing in this case. The main reason the current is increasing is there's nowhere to dissipate that power. So the current can't remove itself. However, I'm going to show you one more trick. I'm going to change this to 10 ohms, and that's going to give us the ability to dissipate power. And watch what's going to happen. The current is eventually going to disappear because every time the current comes through and strikes that 10 ohms, some of the power is going to be wasted, and there's nothing to replenish that power. And so if I wait long enough, it's actually going to take some time. Let me make this go faster by making it 50 ohms. If I wait long enough, this voltage and current will both go to 0. Let's watch that happen. All right. All right, now set that voltage to 0, and here it is. Now we'll see that voltage go to 0. Now, in the prior case, when this was still 1 volt, you can see that it will eventually steady out to 0.5 volt being on the load. All right, so let me just recap the steps to solve one of these initially charged lines. All right, and just kind of recap this. All right, step number one is pretend there's no transmission line, right? This is something you probably would enjoy doing anyways. Step number one is remove the transmission line and replace with 2 wires. Right, go back to the circuit analysis that you would have done prior to this class. Pretend there's no transmission line, replace with 2 wires. And then more importantly, you want to determine the voltage and load the voltage and current on the load, right? VL and IL. Okay. Step 2 is determine the initial V positive and V negative, right? The steady state positive and negative going waves after all those back and forths have finished out. All right, where again, V positive equals VL plus Z0 IL divided by 2. You will have figured out what VL and IL is in step 1, so just plug them in here. And V negative equals VL minus Z0 IL divided by 2. All right, once you finish with step 2, you want to deduce which one will change either V positive or negative, right? Determine whether V positive or V negative will change, and where will it change? It will change, spoiler alert, wherever you made the change, wherever you opened or closed the switch. To determine whether V positive or V negative will change and where. Okay, that's step 3. Step 4 is determine a new value of either V positive or V negative based on your answer to number 3. Step 5 is take the difference, the delta, between step 4 and step 2, right? Whichever one has changed between V positive and V negative, figure out by how much it's changed. If it went from 3 volts to 2 volts, then the delta would be -1. If it went from 6 volts to 9 volts, the delta would be +3, right? So figure out by how much it has changed. And finally, you set up a bounce diagram. And launch a wave with the value from step 5. And then track that wave. And carry it on, and you will eventually reach your steady state, but you're going to see how it's going to get there. How you'll eventually reach a new steady state. All right. So armed with these steps, you should be able to hopefully solve the negative parts or the discharging portion of transmission lines with digital logic and circuits. In the next video, I'm going to go through a numerical example so you can see this as it actually happens.